Hello everyone. This is the final project presentation for the course ECE 544 Silicon Photonics for Computing Systems. The title of the project is Optical Switches, Ring Resonator Switch in comparison with MZI based switch. My name is Gautam Reddy and I will be presenting this project. Coming to the introduction of the project, the demand for optical switching has increased a lot in recent years because of the increase of optical interconnects in high-performance telecommunication networks and modern data centers. State-of-the-art electronic switching techniques have bottlenecks such as scalability, bandwidth, switching speed, data rates, and power consumption. To overcome all these bottlenecks, optical switches looks to be a promising component for the next generation optical networks. The reason why this project is chosen is that one of the basic operations in most of the modern systems is switching networks. Today's electrical technology has few limitations to increase the switching speed. Hence, the project aimed on designing an optical switching network and analyze the results. Now coming to the objectives of the project. First, we'll try to understand about the optical switching networks. Then, we'll design a 4x4 optical switching network, optimize the design to get the best performance out of it, and then obtain the results and try to understand and analyze the results. An optical switching network is a network or a structure in which the flow of the optical signal can be controlled. Now, the overview of the project is we will be designing a 4x4 optical network. What does a 4x4 optical network mean? It means the structure which has 4 inputs and 4 outputs with a different components in between, which will help to control the flow of optical signal. In this design, the flow of the optical signal can be controlled from any input port to any of the output ports. At the end, the results from all the output ports will be compared and analyzed. Coming to the methodology of the project. My initial design to make a 4x4 optical switching network was to use multiple waveguides as input and output ports and ring resonators as frequency selective filters. But this design has a large footprint and multiple connections, which will be considered as not as a practical design. Hence, I started with a 2x2 optical switching network by using bidirectional ring resonator circuit and then expand it to design a 4x4 network using ring resonator and directional coupler. We can see the design of the optical switching network on the right side of the presentation. We have used 2 directional couplers and a ring resonator in this design. There are 4 input ports, 2 on the left and 2 on the right. And there are 4 output ports, 2 on the left and 2 on the right. These input and output ports will be numbered and shown in the future slides. We have also used a frequency domain power monitor, which will show us the profile of the whole design for different simulations. And also we have 4 monitors. Each one is placed at the output ports to extract the results. Initially, I was not able to control the flow of the optical signal between all the 4 output ports. I was able to control the signal between 2 input and 2 output ports, but not all of them. So I tried different techniques to resolve this issue, like changing the gap between the ring resonator and the waveguides which are on the directional coupler and changing the gap between the waveguides in the directional coupler and the radius of the ring. But none of these techniques worked for me, so I had to use other techniques to resolve this issue. The solution that I came up for this issue was to create a custom material in numerical charge. Numerical charge is a software that is similar to the numerical mode, where we can create custom materials and import them to numerical mode. So the material that I have created changes its refractive index with respect to voltage applied. You can see in the figure that there are three different materials used for this design: a blue one, light gray, and a dark gray ones. The blue is a silicon, the light gray is a metal, and the dark grays are the silicon dioxide, which are the substrate. When we apply voltage to the metal, the refractive index of the silicon changes. For this project, I have applied -10 to +10 voltages, and the refractive index of the material has changed from -2 to +2. That is, if the refractive index was 3.6, then it can be changed from 3.4 to 3.8. Once this was done, the data of the material was exported and saved in a MAT format. This MAT file can be used in numerical mode by creating a new material and importing the same file into the mode. Then a script was written to run simulations for different refractive index of the material by changing the voltage, then for the different gaps between the ring and the waveguide, for different gaps between the waveguides and the coupling length. After these simulations and obtaining the results, the best parameters for the better performance were obtained. That is, the gap between the ring and the waveguide was 150 nanometer, the gap between the waveguides is 100 nanometer, and the coupling length was 3 micrometer. The refractive index of the material will be changing, and that will be explained in the next slide. On the right side, you can see a figure of the design, and there are totally 8 ports. The sources have been removed from the figure to make it more clear. There are 4 ports numbered as 1, 2, 3, and 4 in blue color, which are the input ports, and the same on the opposite sides, that is 1, 2, 3, and 4 on the red are the output ports. Now let me explain how the simulation works and how we can control the flow of the optical signal between all these ports. In this figure, you can see that there are 3 waveguides which are blue in color, and one of them is the ring waveguide. They have the blue color because these are the materials that have been imported by the numerical charge, and the refractive index of these materials can be changed by applying the voltages on the electrodes on these materials. Now let us consider a source at input 1, and we'll check the possibility of all these things for outputs 1, 2, 3, and 4. To control the signal from input 1 to output 1, what we have to do is change the refractive index of this surface, this blue surface. Then by changing the refractive index again, we can control the signal flow from input port 1 to output port 2. To get the optical signal from input port 1 to output port 3 and 4, we have to change the refractive index of the ring and the material which is right below the ring, which is in the blue color. Once we change the refractive index of the ring, the light from input 1 will not go into output 1 or 2, and it will start going into the ring. and the decision between 3 and 4 can be made by changing the refractive index of the bottom part of the ring below the ring resonator. Similarly, for all the other input and output ports, we can control the optical signal by changing the refractive index of each of these three uh, blue color materials that we can see in the figure. After running different simulations for the change in the refractive index of all the three parts and the gaps between these components, the best possible combination is chosen and the results have been obtained according to the best possible combination. Now coming to the results of the project, in these figures we can see that the optical signal is or the top profile of the design is shown. From the image on the left we can see that the optical signal has traveled from input port 1 to output port 1, and on the second figure we can see that the signal has traveled from input port 1 to output port 2. These figures were taken at the highest point of resonance, and the peaks and the resonant frequencies can be seen in the next figure. Here we can see the transmission graph of the output port 1 and output port 2 on the left and the right respectively. From these two figures we can observe that the output port 1 and output port 2 are complementary to each other, so we can easily control the signal by choosing a proper resonant frequency and the refractive index of the material from the design. Similarly, we can see the results of output port 3 and output port 4 in these figures. On the left hand side, we can see that the optical signal is sent from input port 1 to output port 3, but a small amount of loss is seen in output port 1. Many different simulations were run and many different tweaks were made to minimize this optical loss, but this was the best possible output that I could get from the design. And the maximum output power is seen in the output port 3. On the right hand side, we can see that the signal is sent from input port 1 to output port 4. Here we can see that there are a lot of losses between all the ports, all the output ports. But the maximum output is seen from the port 4. I have chosen input port 1 to run all the simulations because that was the worst possible scenario for this design. These are the transmission graphs for the output port 3 and output port 4. We see that these two are not complementary to each other because to get the output at 3 and 4, the ring resonator has to carry the optical signal, and that happens only when there is a resonant frequency for the ring resonator. So these two will be the same, but the signal can be controlled by the changing the refractive index by applying different voltages at the design. So to conclude this project, we can say that after running different simulations and obtaining the best parameters, the design has worked pretty well for 3 out of 4 outputs. And we can see some small amount of optical losses at the output port 4. But our design has a very small footprint. So these are the trade-offs when we have small footprint and not use multiple ring resonators. Thank you so much for listening. And these are the few references for the project. Thank you.